Hello. So this will be a review for test 2, and these questions come from the practice test. So I'll try to get through roughly half of this, and so I'm going to skip question 1. Question 1 is to find the derivatives of two functions using the limit definition. So if you remember the definition of the derivative from test 1, using the limit of the difference quotient. So we covered that on test 1, and we had a good example of that. The very last question, of course, was to find the derivative of 1 over x using the definition. So yeah, it's, if you want to try one, try part B, maybe using the definition. It's another rational expression. Oh, I'm sorry. That's one I think you did for homework. So x over x plus 2. But like I say, I'm not going to ask find the derivative using the definition on test 2. Rather, I want to make sure you understand the rules of the derivatives, right? The sum rule, product rule, quotient rule, chain rule, power rule, all those rules, right? So on the test, I can ask you a bunch of these types of questions. Find the derivative using the rules, right, rather than the definition. Okay, so let's just look at A very quickly. Y is equal to 7 over x cubed plus 12 cube root of x squared. So before you even try to use any of the rules, you might want to rewrite this in an easier way to use the rules. So this is 7 times x to the negative 3 plus 12 times x to the 2/3. Right. So again, that's not the derivative. That's just the original expression. This is still equal to y. But now we can use the power rule, sum rule, constant times function rule, right? So now the derivative, which is dy over dx, or if you prefer, y prime of x, but I'm usually going to use dy over dx here. So this is 7 times negative 3 x to the negative 4 plus 12 times 2/3 x to the, 2/3 minus 1 is negative 1/3. And then just to multiply all this out, we're going to get negative 21 x to the negative 4 plus 8 x to the negative 1/3. And yep, you can leave it like that. Or if you want to write it in terms of radicals, you can do that. Let's just do it here. So negative 21 over x to the 4, and then plus 8 over the cube root of x. Right. And no need to go any further. You don't have to get a common denominator or anything like that. So this is fine. All right, let's do B. Let's do part B as well. So B is that mess there. Okay, so let's copy it down. F of x is equal to x squared minus 4 times the square root of 25 minus 6x minus x squared. And again, immediately I would write this second factor here in terms of an exponent. In this case, 1/2. So let's write it negative x squared minus 6x plus 25 to the positive 1/2, right? So here, we're really forced to use the product rule, right? There's no way to simplify this in any reasonable way. So now to take the derivative, which is f prime of x, make sure you know the notation for that, right? I suppose you could write df over dx, right? Some books write derivatives that way, but I prefer f prime of x. Right, so product rule, right? First times the derivative of the second, plus second times the derivative of the first. Now, you don't have to write this out, of course. If you'd rather take these derivatives here, right, and just do them in your heads, that's fine. Especially this last one here, that's just 2x, right? So, again, I'm going to write it out maybe this way one last time, the long way. And now, let's just take the derivatives. So, let's see, we're going to get, oh, did I make that negative? Sorry. Yeah, this here should be a positive 1/2. When we take the derivative, of course, it'll become a negative, right? So this is positive 1/2 times negative x squared minus 6x plus 25 to the negative 1/2. Now we need the chain rule, right? Now we have to multiply by the derivative of this, which I'm not going to write d over dx again. We can take the derivative of that in our heads, right? It's negative 2x minus 6. Okay, so this is by the chain rule, right? In other words, it's the derivative of what's inside the parentheses here, right? All right, second term, so plus. We just keep this and then multiply by 2x, right? Because the derivative of this, of course, is just 2x. So I'm going to put that in front already. Oops, minus 6x, right? Let me try that again. Negative x squared minus 6x plus 25 to the positive 1/2, right? Okay, but we can't leave it like this, right? We got a lot of work to do to simplify this. And first thing we'll do is we'll just stick with the x squared minus 4. There's nothing wrong with that. But then we can multiply 1/2 times negative 2x minus 6. Yeah, so this times this is just negative x minus 3. Right. And then why don't we take this downstairs? This is going to be divided by the square root of, I'll leave it as negative x squared minus 6x plus 25. Originally was 25 minus 6x minus x squared. Again, that's just backwards. We like to put the biggest power in front, even though there's the negative coefficient there. That's fine, right? And then for the second term, not much we can do here. Just write 2x times the square root of, negative x squared minus 6x plus 25. So, and this is all over 1. And maybe in this case we should get a common denominator. The common denominator here, of course, is just the first denominator. So we'll multiply numerator and denominator for the second term by that. (6x plus 25). And you can see that these two square roots, when you multiply square root times a square root, you just get that factor under the square root, right? So let's see what we have so far here. And I'm tempted to FOIL this out up here. I think let's do that. All right, so we're going to end up with negative x cubed minus 3x squared plus 4x plus 12. And then here we're going to get 2x times negative x squared minus 6x plus 25. And then all of that will be divided by the square root. Negative x squared minus 6x plus 25, right? And then distribute the 2x here. So I need a little more space. I forgot the square, right? Negative 3x squared plus 4x plus 12. And then minus 2x cubed minus 12x squared. And then plus 50x. all divided by the same square root. I think I'm going to go back to 25 minus 6x minus x squared. Same thing, right? Just change the order. And that's an x, not a y. All right, and then combine like terms in the numerator. So negative 3x cubed, and then negative 3x squared minus 12x squared is negative 15x squared. And then plus 54x plus 12, all divided by the same square root. And while we could try to factor the numerator, I don't think we're going to get very far with that. So I think that's probably as far as we want to take this here. Yeah, that's as simple as I think we can get it. And I just noticed in the answer key, I kind of left it like this up here. I did not get a common denominator. Okay, so that's fine too. That would have been okay. In general, though, you do want to get a common denominator most of the time. And in this case, I don't think it was that unreasonable to simplify all this. All right, so that was a long one. That was part B. And then, should we do C? Again, I'm not going to do all of these. I think C is just an application of the chain rule. I think we can do that one very quickly here. So C, g of t is cosecant of square root of t, right? Or cosecant of t to the 1/2, right? Because we're going to need the power rule here. So nothing we can do to simplify it, so let's just take the derivative. The derivative of cosecant is negative cosecant. Yeah, okay, I'll leave it as square root of t, right? Cosecant times cotangent. And then by the chain rule, then we multiply by the derivative of square root of t, which, right, that was the whole point of this, to write it as t to the 1/2 and use the power rule. But we've done that before, right? And that's just 1 over 2 square root of t. So I think I wrote this as negative cosecant square root of t, cotangent of square root of t, all over 2 square root of t. So that's fine. If you insist on leaving it with these at t to the 1/2, then sure, you can write this as, let's see, negative 2 t to the negative 1/2 cosecant of t to the 1/2, parentheses, yep, and then cotangent of t to the 1/2. And I would be perfectly happy with that too. It's not in the answer key, but it's a perfectly acceptable way of writing it. And then part D is kind of a long one. Yep, let's do it. So part D, oops. So let's see, U is equal to, in parentheses and then other parentheses, 2x plus 1 cubed plus x, and then that's squared, and then plus 4x. Okay, so one option is to multiply all this out. I wouldn't. I would just take the derivative, or u prime of x, by, right, first of all, it's a sum, so we just need the sum rule, right? It's the derivative of the first plus the derivative of the second. Now, what's the derivative of this? Well, it's to the power 2. So by the power rule, it's just 2 times all of this to the 1. And then by the chain rule, times the derivative of the same thing. Right. And then plus the derivative of 4x, of course, is just 4. So now we still have 2 times 2x plus 1 cubed plus x to the 1. And now what's the derivative of all this? Again, sum rule here. So derivative of the first is 3 times 2x plus 1 squared. And then by the chain rule again here, the derivative of 2x plus 1 is 2. And then plus the derivative of x is 1. So not much else we can do here. I would still leave this as 2x plus 1 cubed plus x. And then here, 2 times 3 would be 6. So 6 times 2x plus 1 squared plus 1. And that is good enough. And I hope that's the answer in the answer key, because I really would not try to multiply that out any more than it is. Yep, that's it. Oh, I forgot the plus 4 here at the end. Oops. So plus 4, and then squeeze that in here, plus 4. Okay. Yep. So that's the answer I have, and that's plenty good. That's good enough. All right, so what's next? E. Oh, E is really easy. You really can't mess this one up here. So E, what is it? F of theta is equal to cosine squared theta plus sine squared theta. And, well, I'm going to do it the long way. If you don't know what this is, well, that's too bad, because this is very familiar. It should be. But let's say you've completely forgot what this is. Then let's just work it out, right? So remember, this is cosine of theta squared plus sine of theta squared. And by using the power rule, we get 2 times cosine of theta. And then by the chain rule, the derivative of cosine is negative sine, plus 2 times sine theta. And then the derivative of sine of theta is cosine of theta. And notice what we get here. We get negative 2 sine theta cosine theta, just switch places, plus 2 sine theta cosine theta. And even though these are, just sine of 2 theta and negative sine of 2 theta, they add up to 0. So the answer is 0. But of course, the quick way to do this, right, cosine squared plus sine squared, you should know what that is. That's 1 by Pythagorean identity, right? So really, you're just taking the derivative of 1, which is 0. So see how much faster that is, but you get the same answer whether you do it the long way or the short way. Right? And the long way wasn't that long either. It's just not necessary if you know that the Pythagorean identity, right, that the function you're differentiating is really just a constant. It's just 1. All right, so that brings us to F. And I don't think I'm going to work it out for you. Well, maybe I will. But I'll give you certainly a pretty big hint here. Right. So this looks like a quotient rule problem, but it really isn't, right? So before we take the derivative, notice the numerator is sine x minus tangent x to the power 1, and the denominator is really sine x minus tangent x to the power 1/3. And what's in the parentheses is the same. So just by using the rule of exponents, this is sine x minus tangent x to the 1 minus 1/3, which is 2/3. And now you just use the power rule and the chain rule to take the derivative. So 2/3 times tangent x sine x minus tangent x. Right, to the negative 1/3. And then times the derivative of sine is cosine. The derivative of tangent is secant squared. Good enough. Okay. G is, well, again, so square root of x plus the square root of x plus 4. Right. So first things first, this is x plus 4 to the 1/2, and then again to the 1/2. So to take the derivative, yep, no way to simplify this. Not real, well, maybe there is, but it's not that helpful, I think. Just take the derivative, right? Use the power rule. And then the chain rule. So the derivative of x is 1, and then the derivative of x plus 4 to the 1/2. So 1/2 times x plus 4 to the negative 1/2. And then the derivative of x plus 4 is just 1. So we don't need the 1 there, but we'll simplify that. And actually, there's really not much to do there, so I regret writing the 1. Well, yeah, I'm just going to leave it. In fact, let's just do this. And I think, do we need a parentheses? Where do we need the parentheses here? Right here. So forget that. All right, good enough. H is theta plus cosine theta over 1 minus sine theta. Z, right? Is that right? Oh, plus in the numerator. Theta plus cosine. Okay. So unlike part F, because it looks a little similar to F, except, yeah, these are not the same. So not much we can do to simplify this. Okay, so let's just take the derivative with respect to theta. Quotient rule, right? Low d high minus high d low. I think this is the first time we actually had to use the quotient rule, at least for these problems here. So 1 minus sine theta, coincidence, right? Minus high d low, right? So numerator, and then the derivative of the denominator is just negative cosine theta, all over the denominator squared. All right, simplify. So notice what we can do here in the numerator. We can either expand this out, or notice that it's just 1 minus sine theta squared. And then let's do a plus cosine theta times theta plus cosine theta. Okay. So you can do two things here, right? You can notice that the 1 minus sine theta squared is the same in the numerator and denominator, so that's just 1, plus cosine theta times theta plus cosine theta, all over 1 minus sine theta squared. So I think I wrote it two different ways. That's one way. Or you can expand out the numerator and just write it as one big fraction, right? So 1 minus 2 sine theta plus sine squared theta. And then, multiplying this out, we get plus theta cosine theta plus cosine squared theta. And no reason to multiply out the denominator. I will leave that as 1 minus sine theta squared. But in the numerator, we can do a few things here, right? Notice we have sine squared plus cosine squared, which is just 1. And then 1 plus 1 is just 2. So that's just 2 minus 2 sine theta plus theta cosine theta, all over 1 minus sine theta squared. So I think I wrote it both ways. Yep. Either way is fine. I wouldn't say one is simpler than the other. It's just your preference. And then what was it again? F of x, yeah. Is equal to tangent of cosine of sine of x. Okay, so we're not multiplying, right? This is not a product rule. This is not tangent x times cosine x times sine x. Although that's a good problem too, that's not this one here, right? So just make sure you know the difference here. So what do we do? So in this problem, we're just going to take the derivative of tangent is secant squared of cosine of sine of x. And then by the chain rule, we take the derivative of cosine of sine of x. Okay, so what's the derivative of cosine? Negative sine of sine x. And then by the chain rule again, the derivative of sine x, which is just cosine x. So I'm going to do a couple things here. I'm going to pull the negative in front, the cosine in front, and then I'll do the sine of sine of x. And finally, the secant squared of cosine, of sine of x. And that's probably how I wrote it in the answer key. And, well, might as well do J. Actually, I'm really not going to do J here, but I will get it started. So J is f of v is equal to 1 over the 5th root of 1 plus 2v minus v cubed plus v to the 5th. It's a 5. And so before we take the derivative, we might want to write it this way. I'm going to put the v to the 5th minus v cubed plus 2v plus 1, all raised to the power negative 1 over 5. So now we just use the power rule with the chain rule. So negative 1 over 5 times v to the 5 minus v to the 3 plus 2v plus 1. And then negative 1/5 minus 1 is negative 6 over 5. And then the chain rule, right? So 5v to the 4 minus 3v squared plus 2 plus 0, right? So that is the derivative. And so there you go. I think we did all of them, right? So that's number 2. Let's go on to number 3. Okay, so we want to find the second derivative of this. So we want to find f double prime of x, right? Well, first we have to find the first derivative, and that's not hard. 5x to the 4 plus 12x squared. And then, wait, the derivative of cosine is negative sine, so negative is positive, right? Plus sine. So now we can take the second derivative, so that's 20x cubed plus 24x plus cosine of x. So very reasonable. Before we go on, maybe let's do something a little more intricate. How about g of x is equal to, let's do tangent of 3x. And the question is to find the second derivative, right? So to find the first derivative, well, we know tangent is secant squared. And then don't forget the chain rule. We have to multiply by the derivative of 3x, which is just 3. And so maybe we should bring the 3 in front, because it is just a constant. Right. And now we need the derivative again. So how do we take the derivative of this? Well, we might want to write it as secant of 3x squared. So 3 times 2 times secant of 3x to the 1. Oh, don't put a 1 because, well, it looks like a prime. It looks like a derivative, right? And then the derivative of secant of 3x by the chain rule. So 3 times 2 is 6. times secant of 3x. And then the derivative of secant is secant times tangent. Yeah, secant times tangent. But again, the derivative of 3x is 3. So we need another 3 here. And then 3 times 6 is 18. And notice we're going to have secant 3x times secant 3x. So that's secant squared of 3x times tangent of 3x. And I might have switched the order here. Doesn't matter, of course. I'll put the tangent first and then the secant squared, but it doesn't matter. So either way is fine. Okay. Yeah, so this wasn't on the practice test, but it is a good problem. So you might want to keep keep that in mind when you have tangent or cosecant or secant or cotangent. Taking the second derivative usually involves some sort of a product rule of some kind, or a chain rule or double chain rule. So, okay, moving on. Okay, so number 4. Suppose we have the position function, 3t squared minus 4 squared of t. Positions in meters, time is in seconds. So question A, find the average velocity in the first 3 seconds. Yeah. So not a calculus question at all, right? So the average velocity, right, it's rise over run. And the first 3 seconds, right? So we're going from t equals 0 to t equals 3. Be careful you don't go from 1 to 3, because that's only 2 seconds, right? So we're just going to subtract s of 3 minus s of 0, all divided by 3 minus 0, right? And so what's s of 3? It's going to be 3 cubed, so 27 minus 4 squared of 3. And then what's s of 0? 0 minus 0 is 0, right? Divided by 3. So not much we can do here. 27... Just hang on. 27 minus 4 squared of 3 all over 3. So that's the exact, of course we need units here, right? Meters per second. There we go. And it also says round to the nearest tenth, so tenth of a meter per second. So my calculator says 6.69. So approximately 6.69 meters per second. Oh, I'm sorry, nearest tenth. So 6.7 meters per second. Fair enough. And then part B says find the instantaneous velocity at t equals 4. I just wrote velocity, but that means instantaneous velocity here. So either way, so this is instantaneous. So what do we need for the velocity after 4 seconds? Well, we need the derivative of the position. So before we plug in 4, we need to take the derivative, which is 6 times t minus 2 divided by the square root of t. So plugging in 4, we get 6 times 4 minus 2 over the square root of 4, right? So 24 minus 1 is 23 meters per second. Okay. And then part C is to find the instantaneous acceleration. But it'll just say acceleration probably at t equals 4 seconds, so same time. Okay. So acceleration just means we need the second derivative of the position. But we already took the velocity, so we only need the first derivative of the velocity. Oops, I'm not going to plug in 4 yet, sorry. We want the velocity, the acceleration as a function of time. Either way, right? So what do we get? We get 6, and then let's see. This is going to be 6t minus 2t to the negative 1/2. So negative 2 times negative 1/2 is positive 1. And then we get t to the negative 3 over 2. So this is 6 plus 1 over t squared of t. Either way. Oh, and then plug in 4, of course. So 6 plus 1 over 4 root 4 is 6 plus 1 over 8. So 6 and 1/8, or better yet, 49 over 8. And this will be in meters per second squared. Or if you prefer, 6.125 meters per second squared. Okay. And then part D, when was the object stationary? Stationary meaning not moving, right? Not moving meaning its velocity is 0. So when is the velocity 0? So let's go back to the velocity function, 6 times t minus 2 over square root of t. When was that equal to 0? So solve that for t. Oh, I have just enough space, right? So add the 2 over root t to both sides, and then multiply by the square root of t. Let's do that down here. Right. So this is t to the 3/2 is equal to 2 over 6, which is 1 over 3. So we get that t is equal to, let's see, 1/3 to the power 2/3. Or in other words, 1 over the cube root of 9. Yeah, so what is that? Sorry, I get about 1/2. It's about 0.48 seconds. Okay, so that was the time at which the object was not moving. Okay, number 5. We're given a function, and if it's too small, let me write it down again. It's a piecewise defined function. It's ax squared plus bx plus c. Well, we know c is 1 here. So c is 1, and that's a b, not a 6. Right? And this is going to be true if x is less than or equal to -1. And it's negative x squared minus 3 if x is greater than -1. And the question is to find a and b. So, sorry, I know that looks like a 6. A and b. So that f is differentiable. Okay, so that's the question. So differentiable means the derivative exists, right? So I think we can see that both are quadratic functions, and quadratic functions are differentiable. So the only issue is what happens at -1, right? So they're differentiable everywhere else, but what about -1? So that's where it's divided, right? Okay. So before we take the derivative, there's actually two things we need here, because we're looking for both a and b. We're looking for two variables here, a and b. Right? And so if we just use the differentiable condition, it's not going to be good enough. Right? Differentiable implies continuity, so it also has to be continuous. So where's f continuous? Well, everywhere, except maybe at -1, right? So let's take the limit from the left. And that has to be the same as the limit on the right. -1 though, right? Yeah. Right, and this is what you did on your first test. Some of you forgot to write limits, but you know, you mostly had the right idea, that the functions have to match from the left and right. So the left-handed limit is going to be what? A times -1 squared plus b times negative 1 minus 1. And if you take the limit from the right side, you get negative 1 squared minus 3. So be careful, because there's a lot of negative signs. This is a minus b minus 1, and negative 1 squared is 1, but there's still a negative in front. So negative 1 minus 3 is negative 4. And now I would add the 1 to both sides, and you get a minus b is equal to negative 3. Keep that in mind. That alone, of course, is not enough, right? Because a could be 0, b could be 3, a could be 1, b could be 4, right? So we only did continuity here, right? We didn't do differentiability yet. So now let's take the derivative. I should use a different color. So the derivative is what? Right? It's going to be 2ax plus b plus 0, right? And that's if x is less than negative 1. And it's just going to be negative 2x minus 0 if x is bigger than negative 1. Okay. Now, some of you might be thinking, wait a minute, wasn't this a less than or equal sign up here? So how did I go from that to just strictly less than? Why didn't I put in an equal sign here? So, right, that has to do with the fact that this is the derivative, not the original function, right? The original function was defined at negative 1, right? So in other words, we could have evaluated f at negative 1, and of course we would just get a minus b minus 1. But for the derivative, that's not clear, right? And in fact, depending on a and b, f of negative 1 might not even exist, right? It depends on a and b, of course. That's the whole question. When is it differentiable, right? So yeah, for a whole bunch of a and b, this might not even be true. So in general, you really have to get rid of that equal sign here. We just don't know when it's going to be, which of these it's going to be equal to. We want them equal to both, right? So we do the same thing here. We take the left-handed derivative and the right-handed derivative, right? So approaching negative 1 from the left, for the derivative now, is just going to be negative 2a times negative 1 plus b. So that's 2a plus b, right? And then the limits coming from the right side for the derivative, negative 2 minus 1, which is just 2. So again, these two things have to be equal. Right? So 2a plus b has to equal 2. So the first condition here was for being continuous. The second condition was for being differentiable. Now put them together, solve that system, and you have your a and b. And again, I should really let you do that, but so go ahead and pause the video and work that out. Hang on. All right, so there's a mistake here, and I think most of you probably figured it out. Sorry about this. This was a plus 1. I don't know why I changed that to a minus 1. So this should be a plus 1. This should be a plus 1. So what I should have done here is, instead of adding 1, I should have subtracted 1. And that means this should be negative 5 here. So this negative 3 should be a negative 5. There we go, negative 5. Now go ahead and work it out. And here's what you should get, right? You can just add the two equations to eliminate b. You get 3a plus 0 is equal to negative 3. So just divide by 3. That tells you that a is negative 1. Right? And that's still not right. Okay, let's check what I did here. Plus b, no, that's right. So the derivative is 2ax plus b. Yeah, 2a, oh, 2ax plus b. Okay, there we go. This minus sign should not be there. I don't know where that came from. I'm just sloppy today. So that's a positive 2a times negative 1, which makes this a negative 2a. So I'm missing a lot of minus signs here. So there should be a negative 2a plus b here. Phew. Okay, now we can work it out, and hopefully this is correct. All right. Sorry about that. I guess I'm just a little tired here. This is negative a plus 0 equals negative 3. So a is positive 3. And if a is 3, subtract 3 from both sides. And we get b is, well, let's see. We get negative b is negative 8. So b is positive 8. Okay. So a is 3, b is 8. And that's what the answer key has, so let's go with that. So I think these are right. I don't know how that got moved. All right, so that was number 5. I mean, you know, very easy to make these little mistakes. I know I'm not the only one. Everyone makes these little mistakes every so often. And yeah, of course, if you know, that'll give you the wrong answer if you just miss a minus sign, as I did, and I did it twice here, right? Once up here, and then once again right here I had a minus where there shouldn't be one. So, okay. All right, let's try the next one then. Okay, so I hope this one goes a little bit better. Find the equation of the tangent line to the graph of y equals, that's a cube root of x squared plus 2x plus 1 at the point 7, 4. Okay, and they didn't have to give us the 4 here, right? If you plug in 7, you should do this. That's a 1, right? This is 49 plus 14, well, 50 plus 14 is 64, and the cube root of 64 is indeed 4. So they were being generous in giving us the 4. They could have just said at x equals 7, and then you would have to figure out the y is 4. Okay, so again, I know most of you like to use y equals mx plus b, but I'm going to use the point slope formula here. It's all the same to you. Particularly because we have a point, right? Y is 4. We don't know what m is yet, but x0 is 7. So how do we find m? Yep, derivative, right? Slope of the tangent line is the derivative at x equals 7. Right. So what's the derivative? Well, before we take the derivative, we might want to rewrite y as x squared plus 2x plus 1 to the 1/3. Or you should recognize x squared plus 2x plus 1 is just x plus 1 squared. So y is really just x plus 1 to the 2/3. So now to take the derivative, and I guess I'll do that down here. This is just 2/3 times x plus 1 to the negative 1/3. And then by the chain rule, we multiply by the derivative of x plus 1, which is just 1, right? So, yep, this is just 2 over 3 times the cube root of x plus 1. So, okay. Okay, so now that's that's not our m yet. We have to plug in 7 here. So we'll do that here. So this is 2 over 3 times the cube root of 7 plus 1. 7 plus 1 is 8. And the cube root of 8 is 2. And the 2's cancel, so I guess we just get 1/3. So m is 1/3. And multiply it all out. Plus 4 over 1, plus 4. And this is going to be, let's see, 12 over 3. 12 minus 7 is 5, right? So plus 5 over 3. So that should be the same thing for those of you that used y equals mx plus b. Your b should be 5 over 3. And again, I prefer writing it this way. In the textbook, the answer key might write it this way. So x minus 3y plus 5 equals 0. So of course I would accept that too. It's the same equation, just written in a different way, standard format there. Okay, so let's go on to number 7. So of course I'm not going to do all of these. I think one we pretty much did already. I remember doing this in 2.5. Correct me if I'm wrong. So let's go on to b. b is a little trickier. So this is 2x cubed y plus y to the 4th is equal to pi. Remember, pi is a number. So find the derivative of y, right? With respect to x, of course. So rather than try to solve for y, you're not going to be able to do it. I can't do it either. Just take the derivative of both sides, right? So this is implicit differentiation. Yeah, that's right. 2x cubed y plus y to the 4th. And then the derivative of pi, of course, is 0. Pi is a constant, right? So what do we get on the left side? The left side, first we have the product rule. So first times the derivative of the second plus second times the derivative of the first. And then the derivative of y to the 4th is 4y cubed times the derivative of y, and that equals 0, right? So factor out the dy over dx. We get dy over dx times 2x cubed plus 4y cubed plus 6x squared y equals 0. So I think the next thing is to subtract the 6x squared y from both sides. Right, and then just divide both sides by this entire factor, 2x cubed plus 4y cubed. And then that should be your derivative. Oh, I think we can divide by 2, right? So if we factor out a 2 here, okay, negative 3x squared y times 2. And then we have x cubed plus 2y cubed times 2. Yep. Cancel the 2's. So you're just going to get negative 3x squared y over x cubed plus 2y cubed. That looks good. One more. So I think D is pretty similar to B. Again, just take the derivative of both sides. Don't try to solve for y. C. So we have sine of xy equals cosine of x plus y. So, oh, I'm out of space. Okay, hang on. Okay, so sine of xy equals cosine of x plus y. Again, just take the derivative of both sides. There's no way you're going to solve for y here explicitly. Try that again. Okay, so the derivative of sine is cosine. And then chain rule, we need to take the derivative of xy. So similar on the right, the derivative of cosine is negative sine of x plus y times the derivative of x plus y. Okay, so we still have to evaluate these derivatives here. And this is a product rule, right? First times the derivative of the second plus second times the derivative of the first. Derivative of x is 1. Oh, plus y, right? And the derivative of x plus y is 1 plus the derivative of y. Okay, so that's it. The rest is just algebra, right? So multiply all this out here. This times that times that. Yep. So x cosine of xy. And I really want to write y prime here. Why start now? Okay, and then the right side will just be negative sine of x plus y, and then minus sine of x plus y times the derivative. So we want all the derivative terms on the left. So why don't we add that to both sides? And while we're at it, why don't we subtract this from both sides? Okay, almost done. Factor out the dy over dx. And on the right side, let's factor out the negative 1. We don't have to, but might as well. And then just divide. So let's see. We'll put that first. Now, does that look right? Yeah. So be careful, right? There's a lot that can go wrong here. If you're not careful, it looks like you might cancel these, but these are plus signs, right? They're not factors of the numerator. So no, they don't cancel. Likewise, these are factors, but not of the entire numerator. So the cosine xy doesn't cancel either. There would have to be parentheses here. Then you could cancel the cosine of xy. So no, basically nothing cancels here. That's an x. So this is the best we can do. So yeah, that was a hard one. That was a hard one. Okay, so number 8 is very similar to number 6. Find the equation of a tangent line. So I'm going to do the sort of the non-trivial version of that, number 9. find the points on the graph of this equation here where the tangent lines are horizontal. So what does it mean for the tangent lines to be horizontal? Well, a horizontal line has slope 0. The tangent lines are where the derivative, right? The slope of the derivative. So that means the slope of the derivative has to be 0. So we need to find the derivative, and that's just implicit. You could solve for y here, but you're going to get a plus or minus square root, and that's not pleasant. So as usual, we'll just take the derivative of both sides implicitly. And the derivative of 0 is still 0, right? Now on the left side, you're going to get 4x cubed plus 50y times the derivative of y, don't forget the chain rule, right? Minus 50x equals 0. So solving for the derivative of y, so we'll add the 50x to both sides, subtract the 4x cubed from both sides, and then divide by 50y. Yeah. We could have canceled the 2 here, but we'll do that later. Right. So this is really 25x minus 2y cubed divided by 25y. So just divide top and bottom by 2. Okay, so remember our goal is to figure out where the derivative equals 0. Where does it equal 0? When the numerator is 0. So we just have to solve the equation 25x minus 2x cubed equals 0. And that's not hard, right? Factor out an x. So we get x equals 0 as one solution, and then x squared is equal to, let's see, 25 over 2. Take the square root, don't forget plus or minus, 5 over square root of 2. So we actually get 3 solutions to this equation, right? It's a cubic equation, so you can get up to 3 solutions, and we got 3 solutions. Here they are again, x equals 0, x equals 5 over root 2, and then x equals negative 5 over root 2. Okay. But remember, we're looking for the points, right? A point is not an x. It's an x and a y. So how do we find y? Well, we plug these numbers back into the original equation. Again, we never solve for y here, but I'm going to need to write down the original equation again. Right. And in fact, notice we don't need x. We need x squared. X squared was 25 over 2. And if we square that, we get x to the 4th, which is 625 over 4. So plug those in here, and what do we get? So this is going to be 25 times 25 over 2 minus 25. Oh, wait a minute. Sorry. We don't know what y is. That's what we're solving for. Here's where we plug in 25 over 2 equals 0. There we go. So what do we get? 25y squared. Let's do plus 625 over 4 minus 625 over 2. And that's going to be negative 625 over 4. Right. So add that to both sides. It's positive 625 over 4 on the right. Divide by 25. Sorry. And you get 25 over 4. Now take the square root. We get plus or minus 5 over 2. Okay, so when when x is either positive 5 over root 2, and y will be, sorry, plus or minus 5 over root 2, and when, there we go, x is negative 5 over root 2, y will also be plus or minus 5 over root 2. So we really get 4 separate points here, right? Where x could be positive or negative 5 over the square root of 2, and y is positive or negative 5 over 2. Right. Oh, what about x equals 0? So if we plug that in, then we get, well, 25y squared plus 0 minus 0 equals 0. We get y equals 0. Okay, so maybe 5 points. 0, 0, 5 over root 2, 5 over 2, and then let's do, yes, 5 over the square root of 2, negative 5 over 2, and then we need a negative x, negative 5 over root 2, 5 over 2, and finally negative 5 over root 2, negative 5 over 2. So 5 points where the tangent line is horizontal. And I just looked at the answer and I realized something's wrong here. So notice if x is 0, y is 0. But go back to the derivative. Where did I write down the derivative? Here it is. Well, here. This either way. So it's going to be forgot again, 25x minus 2x cubed over 25y. Yep. So what happens if x and y are both 0? Let's plug that in. You get 0 over 0. Indeterminate, undefined, it's not a number. So there is no slope at 0, 0. Right? The slope is not 0. 0 divided by 0 is not 0. Could be anything, right? It's indeterminate. Right. Same thing as undefined in this case. It's not a number. Okay, so for that matter, for that reason, 0, 0 is not one of those points. It's just these 4 here. Okay, so that's the answer to number 9. And if it helps, if we graph this equation here, you'll see what goes wrong at the origin. So I'm going to do a graph, a very crude graph here, but get the idea. The graph is going to look something like this. That part looked bad. Let me try that again. That's still not great. I'll try it the other way. There we go. Close enough, right? So kind of looks like a dumbbell, and the idea is when x is negative 5 over root 2 or positive 5 over root 2, y is going to be either positive 5 over 2 or negative 5 over 2, 2.5, right? So you have these 4 points where the tangent line is horizontal. In fact, we can draw the tangent line. I'll do that in red. That's horizontal. Kind of missed it there. That's horizontal. That's horizontal. And that's horizontal, right? So 4 points. Those are the 4 answers we got up here. But what's wrong with 0, 0? Because it does look kind of flat here. It does look like this line is the horizontal tangent line. The problem is that the graph crosses itself here, right? Even though it does it like this, when the graph crosses itself like that, that's kind of a bad point then. This point right here is not well defined, right? So even though it looks like the tangent line is horizontal there, according to this derivative here, when x and y are both 0, you don't get a number. You don't get a slope. So for that reason, we really had to get rid of the 0, 0 as an answer. It's not one of the answers, or it shouldn't be. Shouldn't be, right? So think of a graph that crosses itself like this then. Right. So what would you say the slope is at this point? Well, right, you can say maybe it's positive 1, or maybe it's negative 1. But it can't be both, right? So yeah, at these cross points, there is no derivative, right? We don't say it's both. We don't say it's two numbers. And so we kind of just give up and say it's neither. Now this point's a little different over here because it looks like both of them are going to be 0, but it turns out, again, neither. So 0, 0 is not one of the answers. The derivative does not exist at 0, 0. So I hope that helps. And let's keep going. Okay, so number 10 is not supposed to be a difficult one, but it's one that I think a lot of students do have some trouble with. So if u is equal to 5x squared plus 2x, and x is equal to the square root of t, find the value of u, so we're looking for a number for u, when the derivative of u is equal to 8. Okay, so there's a couple ways of thinking about this, right? U is a function of x, right? It's just 5x squared plus 2x, but then x is a function of t, being the square root of t, or t to the 1/2, right? So u is really a function of t. It's a function of a function, right? It's a composition. Right? So the most direct way to do this is to find what u is in terms of t. And that's not hard to do. Just replace x with the square root of t. So you get 5 times the square root of t squared plus 2 times the square root of t. So u is really just 5t plus 2 square root of t. Okay. Now, what's the derivative of u with respect to t? It's equal to 8. So the derivative of u with respect to t is just 5 plus 1 over the square root of t. And that has to be equal to 8. So we can solve that, right? So subtract the 5 from both sides, and you get 1 over root t is equal to 8 minus 5, which is 3. Flip both sides, so the square root of t is equal to 1 over 3. And then square both sides. So we get t is equal to 1/9. Okay, t is 1 over 9. But that doesn't answer the question because they want the value of u, not t. But we know what u is. Right? Here it is. Let me just rewrite it. 5 times t plus 2 times the square root of t. So we can find u just by plugging in t equals 1 over 9. So this is 5 over 9 plus 2 over 3, right? Square root of 1/9 is 1/3. So this is 5 over 9 plus 6 over 9, which is 11 over 9. So that's u, right? This is the value of u, 11/9, right? Or if you prefer, 1 2/9, I'm not picky, but don't write as a decimal, right? Don't write 1.22222 and so on. But that's it, right? So this was, I think, the most direct way to do it. The other way to do it is up here, right? We could have found the derivative of u with respect to t by using the chain rule. But if you can find u directly as a function of t, which we could do here, then there's no need for the chain rule. Right? So we could have used the chain rule to find the derivative directly without finding u as a function of t. So that's a more roundabout way of doing it, but that way works as well. Okay, so that's all there is to it, right? This was supposed to be, this is like the most direct way to do it. Okay. All right, so number 11. Okay, it says a girl flies a kite at a height of 300 feet. So maybe we can draw the picture here. The wind carries the kite away horizontally at a rate of 25 feet per second. How fast is the string being let out of the spool when the kite is 500 feet away? So here's the ground, right? And here's the girl. And here's the string. Here's the kite. Right, and we know that the height of the kite here is 300 feet, and that's a constant. That's not changing, right? So the kite is not going up or down, at least at this moment. Right? Instead, the kite is traveling horizontally this way at a speed of 25 feet per second. Boy, that's a very windy day. That's pretty fast. It's, I don't know, it's like something like 20 miles per hour, right? So it's a pretty, it's a big gust of wind, let's put it that way. So at the moment, that's how fast it's traveling, right? And the kite is 500 feet from the girl, so that means this distance here is 500 feet, right? Right. So you can see what's going on here, right? We get a right triangle. And this is a 3, 4, 5 triangle, so if we call this distance x here, then at this moment, you can check that this is 400 feet. Again, how did I get that? You just solve this equation. Right. In other words, I'm just using the Pythagorean theorem. Make sense? Okay. But then the question is, how fast is the string being let out? So this is the string here. Let's call this length L. It's only 500 feet at the moment, right? So what we're looking for is the rate of change of L with respect to t. Right. So, right, as the kite's flying away here, the next minute it's over here, it's a longer string, right? The string is being let out of the spool. So the length of that string is increasing. Make sense? It's changing. It's getting bigger. How fast is the length getting longer? How fast is the string being let out, right? That's the question. Right. So what are we given? What do we know? Well, remember, x is the horizontal distance, and the kite is only traveling horizontally. So the kite's speed is dx over dt, which is 25 feet per second. Right? So that's given. So what's the relationship between x and L? Well, right, if a is x and b is 300, I called it h for height, but now it's b, right, and c is L, then x squared plus 300 squared is equal to L squared. So the c becomes an L. Right, and 300 squared is 90,000, pretty big number, but that's the relationship, right? L squared is just x squared plus 90,000. So instead of taking the square root, why don't we just take the derivative as it is, implicitly? Oops, That's the second derivative, right? We just want the first derivative. So this will be 2L, right, times the derivative of L. And that's going to be 2x times the derivative of x. And then the derivative of 90,000, of course, is 0. It's a constant, right? And then just solve for L's. Solve for the derivative of L. So divide by 2L on both sides. And cancel the 2's. You get x over L times the derivative of x. So that's the derivative of L. It's equal to x over L times the derivative of x. Right? So that's, well, you think that answers the question, but we want to plug in the numbers now. At this moment, how fast is the length getting bigger here? Right? Yep, so plugging in the numbers. So x was what? X was 400, again, at that moment. And L was 500 at that moment. And dx over dt was 25, right? That was given. So we get 4/5, 4 over 5 times 25, which is 4 times 5 is 20 feet per second. And that does it for 11. So that's how fast the string is being let out of the spool. Okay, going on to number 12. This is also a related rates question. Cylindrical balloon is expanding at a rate of 100 pi cubic centimeters per second. So what are we given? The rate of expansion of the balloon. Cubic centimeters is a volume. So this is the derivative of the volume with respect to time. It's 100 times pi cubic centimeters per second. Right. Its radius is expanding at a rate of 2 centimeters per second. So the rate of change of the radius is 2 centimeters per second. We want to find the rate of change of the height when the radius is 3 centimeters and the height is 5 centimeters. Okay, so that's the question. So what's the relationship between the volume, the radius, and the height for a cylinder? Now keep in mind, this is a balloon in the shape of a cylinder. So the height is getting bigger, the radius is getting bigger, and so the volume is getting bigger, right? So it's an expanding cylinder. So here's the radius, right? Here's the height. So you can look it up. The volume is just pi times r squared times h. And, you know, this will probably be given in the problem, but because it's on the practice test or in the homework, you can always look it up, right? Okay, so we have the derivative, right? So obviously we want to take the derivative. That's v for volume, not velocity, capital V, right? Both sides, so implicit differentiation. So on the left, we just get the derivative of the volume, derivative of v. On the right, this is a product, and it's the product of three things, right? Pi, r squared, and h, but pi is a constant. That can come outside the derivative. So now we just need the derivative of r squared times h. All times pi. So this is a product, right? Product rule. First times the derivative of the second plus the second times the derivative of the first. Again, don't forget the chain rule. The derivative is not 2r, but 2r times the derivative of r. Right? Remember, both r and h are changing. So neither r nor h is a constant. R is getting bigger, h is getting bigger. So yeah, we need both derivatives here, right? And we can simplify this a little bit here. We can distribute the pi, so pi r squared times the derivative of h plus 2 pi h times r, or r times h, times the derivative of r. Okay, and remember the derivative of the volume was 100 pi cubic centimeters per second. So this is all equal to 100 pi. Okay, so what are we looking for? The derivative of h, right? So let's solve for the derivative of h. Right? In other words, we're solving for this variable here. So we can subtract all of this from both sides. So on the left, we still have pi r squared times the derivative of h. And on the right, we have 100 pi minus 2 pi rh times the derivative of h. And now just divide both sides by pi r squared. Okay, so on the left we just get the derivative of h, right? These cancel. And on the right we get 100 pi. Notice we could have, well, even here we could have canceled the pi and everything, but you know, that's not exactly clear. But now if we factor out the pi, we can see what happens. Sorry, 2rh times the derivative of h all over pi times r squared. And sure enough, the pi's cancel. Sorry, that was supposed to be a pi here. Yep. So what's left over is 100 minus 2rh times the derivative of h, all divided by r squared. Yeah, this is in the numerator here. Right. Now we just plug in the numbers. Or let me copy this down up here. Oops. Right. So, yep, I just moved that up here. And then we can plug in the numbers. R is 3, h is 5, and the derivative of r is 2. So we still get 100 minus 2 times r. R is 3, h is 5, and the derivative of h is 2, all divided by r squared, so 3 squared. So 100 minus, let's see, 15 times 4 is 60, and then 3 squared is 9. So 100 minus 60 is 40. So we get 40 divided by 9. And remember, h is in centimeters, and t is in seconds, right? Yep. So this should be 40 over 9 centimeters per second. Right. Or you can do, you know, 4 and 4/9. But again, no decimals, right? 40 over 9 centimeters per second. Good enough. So that's how quickly the height is getting bigger. Every second that goes by, its height is increasing by about 4.5, right? centimeters per second, 40 over 9. Boy, that 9 got weird. Okay. But now it looks like a 7, so. All right, 40 over 9 centimeters per second. So that's the answer to number 12. Number 13. Okay, so air is being let out of a spherical balloon at a rate of 60 cubic centimeters per second. So the rate of change of volume is 60 cubic centimeters per second. But if air is being let out, right, so here's your balloon. Pretend it's a perfect sphere. I know balloons are not exactly spherical, exactly. But in this case, it is, right? So we have the radius. What happens when you let air out? It shrinks, right? So the volume is not getting bigger, it's getting smaller. So this is going to be negative 60 cubic centimeters per second, right? So yeah, when air is being let out, the volume is getting smaller, not bigger. So the question is to find the rate of change of the surface area of the balloon when the radius is exactly 4 centimeters. Okay. So yeah, not a trivial question, right? Because it's not asking for the rate of change of the radius, it's asking for the rate of change of the area. So there's two ways of doing it, right? The direct way is to figure out the volume in terms of the area, right? And that's not a hard problem. But I'm going to do it the indirect way, right? I'm going to, first of all, what is volume in terms of a sphere? The volume is 4/3 pi r cubed. What's the surface area of a sphere? It's 4 pi r squared. Okay, so we need both of these in this problem here. Okay, and if you eliminate r, if you solve for r here and plug that in here, you can get v as a function of a. And actually, that is the most direct way of doing it. Maybe I'll do it that way. I don't know if you would necessarily think of doing it that way. So, all right, maybe I'll do that. Maybe I'll do it later. But for now, what's the rate of change of the volume? So it's going to be 4 over 3 times pi times 3r squared times the derivative of r. And the 3's cancel, so we just get 4 pi r squared times the derivative of r. And you might see, wait a minute, isn't this 4 pi r squared? Isn't that just the area? And sure enough, it is. So that's something you might want to ponder. How do you get this as the rate of change of the volume? Okay. But for our purposes, we get 4 pi r squared times the derivative of r is equal to negative 60. So if we divide by 4 pi r squared, we get that the derivative of r, the rate of change of the radius, is negative 15 over 4. A 60 over 4 is 15, right? So negative 15 over pi r squared. Okay, and when r is 4, so if I plug in r is equal to 4 here, I get negative 15 over 16 pi. Okay, but that wasn't the question, right? The question is to find the rate of change of the area. Well, right, if area is 4 pi r squared for a sphere, right? For a circle, it's just pi r squared. What's the derivative? So it's 4 pi, and then the derivative of r squared is 2r times the derivative of r. So this is 8 pi r times the derivative of r. So that's the rate of change of the area. That's what we're looking for. So now we just plug in the numbers, right? We plug in r is equal to 4. So this is 8 times pi times 4 centimeters, right? And then the derivative of r, well, that's this number here. Right? So plug that in here, and we get negative 15 over 16 pi. Again, the pi's in the denominator. And that should do it. Let's just simplify it, right? So we get 32 times pi times negative 15 divided by 16 times pi. And the pi's cancel. And 32 divided by 16 is just 2. So 2 times negative 15 is negative 30. And that does it, right? But negative 30 what? Right. What are the units? Area is square centimeters. Time is seconds. So there we go. Negative 30 square centimeters per second. So that's the answer. Let me just copy it down up here. Right. So yeah, a little tricky because we had to find the relationship between V and R and then A and R. And as I said, we didn't have to do this in 2 steps. We could have found V as a function of A and then just took the, used the chain rule, right? Right. In other words, if we had V as a function of A, then the derivative of V is the derivative of V with respect to A times the derivative of A with respect to T. And then you can just divide by this to find the derivative of A with respect to T. Right. So it would be the derivative of V with respect to T, which was given, divided by the derivative of V with respect to A. So that's another way to do it. I'm not going to do it that way as it turns out. But if you want to try it that way, you'll see you should get the same answer either way. Right. So that's number 13, and those are the last 3 were the related rates problems. So this was in 2.6, sorry, 2.6. And all right. Okay, so moving on to 14. So we have find the absolute extrema, so that means maximum and minimum, right? So find the maximum and minimum of the function. Well, let's do part A. So the function here is the absolute value of x plus 3 plus 2 times the absolute value of x minus 2 on the closed and bounded interval from -4 to +4. Yeah, I'm not going to do part B because that's a polynomial, and if you go back to section 3.1, I did one just like that there. I did, I think, a third degree polynomial, a cubic polynomial. Okay, so that should not be hard. Part A is probably more difficult simply because we have absolute value, and, well, you may have forgotten how to take the derivative of absolute value, so I will review that. In fact, let's do that now, right? Suppose g of x is just the absolute value of x, right? What's the derivative? Okay, so there's a couple of ways of thinking of this, right? Remember, absolute value of x is a piecewise function. It's just x if x is greater than or equal to 0, and it's negative x if x is less than 0. So the derivative is either 1 or -1, right? It's 1 if x is greater than 0, and it's -1 if x is less than 0. And so the graph is not hard. Right? So the derivative, g prime, that's what I'm graphing here, it's either 1 if x is positive, or it's -1 if x is negative. Now notice there's no equal sign here, right? What happens when x equals 0? There is no derivative. Remember, this is g prime. If you graph g by itself, I'll do that in blue here. Right. You just get this again. Right? So remember what the question is, what's the slope of the tangent line? Well, the line here has slope 1. The line here has slope -1. And you can see that that's all you're graphing up here for the derivative. What's the slope at this point, right? There is none. There's no tangent line there. So, right, so there's no equal sign here. In other words, right, this is a hole in the graph right here, and this is a hole in the graph right here. Right, whatever you do, do not fill in this point because that's not the derivative. The derivative is not 1. It's not -1. Right? It's not 0. It's none of those. Right? So g prime of 0 is undefined. G prime of 0, more specifically, does not exist. Right? So there is no derivative at 0. Keep that in mind. Right? So there's another way to write the derivative of g then. G prime of x. Because it's just 1, you can think of it as x divided by x, right? But what about -1? That would be, well, -x divided by x. So as it turns out, you can think of the derivative as just the absolute value of x divided by x. Okay, and that's the same as what I wrote up here. Right. In fact, you should check that you get the same thing. Okay, now we can tackle the original question here. What's the derivative of it? Right. So remember, if you're finding the absolute maximum and minimum, the first step is to find the critical numbers. And how do we find the critical numbers? Take the derivative, right? Set it equal to 0, and solve for x. So how do we take the derivative? Well, this is how, right? Just take the absolute value of x plus 3. Let's try that again. Right, divided by x plus 3. Now, technically, there's a chain rule here, right? We have to multiply by the derivative of x plus 3, but that's just 1. Right? Same thing here. 2 times absolute value of x minus 2 divided by x minus 2. And then the chain rule says we multiply by the derivative of x minus 2, but that's also 1. Right. So this derivative is just absolute value of x plus 3 over x plus 3, and then plus 2 times, I'll leave the 2 in the numerator, absolute value of x minus 2 over x minus 2. Okay. So now, remember, the critical numbers are where this equals 0. Where does this equal 0? Solve that equation. Yeah, this is not an easy one to solve, right? But go back to the picture here. Whenever you take the absolute value of something, right, whenever you take the derivative of the absolute value, it's either 1 or -1. Now, for f, for this function here on the left, it's probably not going to be 1, right? Because you're multiplying 2, so the derivative might be 2 or 3 or something like that. But it's not going to be 0. The derivative is never 0 here, even at the origin, right? Remember we said the derivative does not exist. It's not 0. Right. So where does this equal 0? The answer is it isn't. Never. It's never 0. Okay. So what does that mean? No critical numbers then, right? Nope. They're definitely critical numbers. But it's not where the derivative equals 0. Remember, critical numbers where the derivative is 0 or where the derivative does not exist. And we know that happens for absolute value. The derivative does not exist at 0. So where does the derivative not exist for f? Well, that shouldn't take you too long, right? Because remember, the issue is why is the derivative of g here, why is that not equal to 0? Or what happens at x equals 0? You're dividing by 0. You get 0 divided by 0, which is not a number, right? So same thing here. When are we dividing by 0? either when x plus 3 is 0 or when x plus 2 equals 0. Wait, I don't think I said that right. Either when x plus 3 equals 0 or when x minus 2 equals 0. Yeah, I'm getting tired. So if I said x plus 2, that's my, yeah, I got to be careful. All right. In any case, we get two solutions, right? We get negative 3 and positive 2. So those are our critical numbers. These are critical numbers, right? Not because the derivative is 0, but because the derivative does not exist. And the same thing here, when you plug in 2, the derivative does not exist. Right? So that's what makes them critical numbers. Okay. Oh, one other thing we have to check, right? Remember, this is on the interval from negative 5 to 3. So remember, this has to be on the interval from negative 5 to 3. Are both of these numbers, negative 3 and positive 2, yep, they are both between negative 5 and 3. So we have to use both, right? If we got x equals 7 as a critical number, well, 7 is bigger than 3. It's not on the interval, so we would ignore that one in step 2. Okay, so step 2 says what? Step 2 says evaluate the original function at negative 3 and at 2, at the critical numbers. So here's the original function. I guess I better write it down again because I can't see it here. So here's the original f. Before we took the derivative, it was just this. Okay. So plugging in negative 3, you get the absolute value of negative 3 plus 3, which is 0, plus 2 times the absolute value of negative 3 minus 2. So we get 0 plus 2 times 5, which is 10. And then when you plug in 2, you get 2 plus 3, which is 5, plus 2 times 2 minus 2, which is 0. So here we just get 5 plus 0, which is 5. Okay, so far. So yeah, so again, you're not plugging these into the derivative. If you do, you get does not exist, right? So that's step 2. Step 3, evaluate the endpoints, right? Plug in the negative 5 and the 3 into the function f. So let's do that down here. We plug in the endpoints, the negative 5 and the 3, into the same function, right? The same blue function here. Sorry, absolute value, yeah. So what's this going to be? Negative 2, and absolute value is positive 2, and then this is negative 7. We make it a positive 7 times 2. 2 times 7 is 14, so 2 plus 14 is 16, right? And then when we plug in 3, 3 plus 3, plus 2 times 3 minus 2. So we get 6 plus 2 is 8. All right, so step 4 is just to answer the question, right? We're looking for the absolute maximum and the absolute minimum of the function f on this interval, right? From negative 5 to 3 here. See that? Yep, absolute extrema, right? Maximum and minimum. Well, it's got to be one of these numbers, right? Either these numbers or these numbers. So out of those 4 numbers, which number is the biggest? Obviously the 16. I hope you can see that. So the absolute maximum is 16. What's the absolute minimum? That's the smallest number, right? That's the 5. 5 is the smallest out of those. So the absolute minimum is 5. Right? And again, that answers the question, right? It occurs at, the 16 occurs at negative 5, which is the left-hand endpoint. And the 5 occurs at one of the critical numbers, at x equals 2. Right? So negative 5, 16 is your absolute, I'll say absolute maximum. And 2, 5 is your absolute minimum. It never hurts to write both, but the maximum value is 16 and the minimum value is 5. Yeah, and this one's actually a good function to graph, and then you can see where you have the maximum and minimum. But I'll let you do that. It's a good thing to try to graph, and you can use your calculator to graph it. All right, moving on. All right, number 15. Given that a function f, which is just sine x, right? So that's our given function, is continuous. Of course, it's continuous. In fact, it's differentiable, but it's certainly continuous on the interval from 0 to pi over 2. In fact, it's continuous everywhere, right? And it's differentiable, right, on the open interval. So we know that. So these are the conditions for the mean value theorem, right? Mean value theorem. So the claim is that there exists a C. So there is a C somewhere between, I'll write it this way, between 0 and pi over 2, such that the derivative of sine, right, which is cosine at C, is equal to f of pi over 2 minus f of 0 over pi over 2 minus 0. And that's just the mean value theorem, right? Ideally, you should know the mean value theorem, but in this problem, they effectively gave it to us. We didn't have to, right? So you don't have to memorize it. It's useful for some things, but I think here it's already given to us, right? So here we have to find C in radians. We can convert to degrees if you want, but they want radians. And then they do want degrees to the nearest hundredth, right? So we'll do both, radians and degrees. Okay. Well, yeah, so the derivative of sine is cosine. You better know that. That just comes up again and again and again, so very useful. And so if we plug in c instead of x, right, we just get the cosine of c. Now what do we get on the right? Right, we get sine of pi over 2 minus the sine of 0 over pi over 2 minus 0 is just pi over 2, right? And sine of pi over 2 is 1. I hope you know that. Sine of 0 is 0. Hope you know that. So this is just 1 over pi over 2, right? It's the reciprocal of pi over 2, so 2 over pi. So that has to equal that. Right, so the cosine of c, my hand's getting tired here, cosine of c is equal to 2 over pi. So what's c? Well, how do you undo the cosine? You can take the arc cosine of 2 over pi, right? Also known as the inverse cosine of 2 over pi. So just use your calculator, right? Oh, so this is the exact value here. This is exact. And now we'll approximate. So just plug it in your calculators. So let's see, I'm in degree mode. So if I multiply by pi over 180, so in radians we get 0.88, what, the nearest hundredth? Okay, nearest hundredth, so this is in radians. And then in degrees, it's about 50.46 degrees. So either way, 0.88 radians or 50.46 degrees. And that's it. That's all there is to it. Not a hard question. Again, when you read it, it's a little confusing because it looks like, you're supposed to know the mean value theorem here. Oops. but you don't have to know it. It's essentially given to you in the problem here, right? They're just asking you to solve this equation here. And we did it. So on the other hand, maybe we will draw the picture here. So here's what they're doing, right? If you look at the picture, if you look at the graph, this is 1, and this is pi over 2. Actually, it is a little further than that, right? So yeah, pi over 2 is right about here. So pi would be here. So the graph of sine looks like this. Right. And of course it continues, right, just back and forth. But we're only going to look from 0 to pi over 2, really. We don't even need the pi here. So 0, 0 is one point on the graph, and pi over 2, 1 is another point on the graph. If we connect those 2 points with a straight line, what's the slope of that line, right? Rise over run. The rise is 1, the run is pi over 2, so your slope is 1 over pi over 2, right? That's the 2 over pi that we got earlier, right? So where on the sine function does the tangent line have a slope of 2 over pi? Well, it's a little more than 45 degrees. It's right about here, right? So right about here, right, it's about 50.5 degrees, 50.46 degrees. If I draw the tangent line here, it'll be parallel to the yellow line. And I know that doesn't look quite right, does it? But it should be parallel to it, yeah. Right. In some ways I made the yellow line crooked, but it looks like this. Right. So they both have the same slope, that being 2 over pi. So we're looking for the c here, the c being the 50.46 or 0.88. Sorry, 50.46 degrees. I hope in your pre-calculus courses, whoever you had for pre-calculus or trigonometry warned you that if you answer 50.46, it's wrong, right? Because it's not 50.46, it's 0.88, and there's a big difference between these two numbers. I hope you see that, right? Yeah, so what's wrong with 50.46? Well, if you don't put the degree symbol here, then if it's an angle, it's 50.46 radians, which we know is ridiculous. It's not even 1 radian, right? It's only 0.88 radians. So yeah, if you don't put the degree symbol here, it's just wrong. So this is 50.46 degrees, not 50.46 radians. So anytime they ask for degrees, you need to put the degree symbol. Otherwise, it's wrong, because I would assume that you're talking about radians. Okay, so yeah. So that's 15. I'll do one more. I'll do 16. Okay, hang on. Okay, number 16. Show that for a quadratic function, so you know what a quadratic function is, right? ax squared plus bx plus c. Little bar there. So it's a capital C. And that may look unusual, right? Usually we use lowercase letters. But you can just see that we're going to use little a, little b, and little c for other numbers. So in this case, yep, we have to use capital A, B, and C for the coefficients of your quadratic function. So, right. So our interval is from little a to little b, and that's, right, already you can see why we can't use little a and little b here, because they may not be the same numbers, right? So we want to show that this quadratic function on this interval, right, the guaranteed value of c using the mean value theorem. So we have to remember what the mean value theorem is, and I know in the last question I said, you don't have to remember it, but here we probably need it. So the mean value theorem just says what? It says that if f is continuous and differentiable, clearly it is, then the derivative of f at little c, not capital C here, little c, lowercase c, is equal to f of little b minus f of little a divided by b minus a. Okay. So here you would have had to look that up if you didn't remember it. So that's what the mean value theorem says. And the question is, we want to show that the value we get for little c here, so hang on. So we have to show that c is the midpoint of the interval. So what's halfway between a and b? In fact, I'm going to draw a little graph here. Oh, that's pretty good. Right. So let's say this is a here, and this is b way over here. Right. So we want to show that c is halfway in between. So you know how to find the midpoint, right? Just add them up and divide by 2. It's just a plus b over 2. That's what we want to show, that the c is right in the middle here. Now the c for what? The c for the mean value theorem, right? Suppose we have a quadratic function. Suppose it looks, oh, I don't know, like this. Yeah, and it keeps going. So obviously we don't need the whole thing here. I'll try to do this. Okay, so that's the parabola here. And so this is up here. This would be f of a. Right around here, this would be f of b. And here's c. Now, we don't need f of c. We need c itself, right? So f of c would be maybe just below f of b, but it doesn't matter, right? Right. So what is this here on the right? What is that equal to? Well, that's the difference quotient, right? It's the rise over the run from these 2 points here. So connect these 2 points with a straight line, as straight as I can. Okay, not bad. Right? So this is the slope, right, of this line here. I'll just call it the yellow line. The slope of the yellow line, right? And we know it's negative looking at it in this example here. Right, remember the green function here is the parabola. That's your f of x. Right, that's your ax squared plus bx plus c. Got it? Okay. So what we want to show is that the c, at this point c here, if we drew the tangent line, right, that it would have slope f prime of c. So if I draw the tangent line, does that look right? Do you buy that this line, this red line here, has the same slope as the yellow line? Looks like it, right? But we have to show that for sure. The graph might be sloppy, right? Right? And in fact, it does look pretty sloppy. Oh gosh, I'm trying to erase the red line here. Yeah, I mean, you know, if I pick this point and use that as the slope of the tangent line, that looks about right too. But then that c would not be the midpoint, right? That's the problem with that, right? So if I draw the tangent line here, how do we know that it doesn't look like this, and then they're not quite the same slope? Okay, so the picture is nice. It gives us a pretty good interpretation, but it's not a proof. It's not a proof. So how do we show it, right? How do we show this? And the answer is to go through the steps here. Go through the mean value theorem. Okay. So first thing is, what's f prime of c? Well, what's f prime of x? It's 2 times a times x plus b. So what's f prime of c? I can do that in green. Oops, got the b here. So f prime of c then, lowercase c, right, is going to be 2 times capital A times lowercase c plus b. Just change the x to the c here, right? Okay, so that's the left side, right? This equals here. What's the right side? I don't know if I have enough space for it, but let's try to squeeze it in here. What's little f of b? It's taking the little b here and replacing the x with little b. So that's going to be capital A lowercase b squared plus capital B times lowercase b plus capital C. And then what's f prime of little a? Same thing, but replace the x with little a's. Oh, sorry, not plus. That's a minus now. So it's a minus capital A lowercase a squared plus capital B lowercase a plus capital C, right? All over b minus a, lowercase b minus a. Okay, yep, so we got to subtract these two things here. So the left side, there's not much we can do to simplify that. It's 2ac plus b. Sorry, that's a lowercase c. Notice, though, we have to distribute the minus sign here. So what we get is ab squared plus bb plus c minus aa squared plus ba plus c. And notice I'm not distinguishing capital and lowercase letters here, but you can see it when I write it out, I hope. Okay. So what's next? So let's collect some like terms here, right? If I put these two terms together and factor out the capital A, what do I get? I get capital A times little b squared minus little a squared. What if I factor out the capital B here? I get capital B times little b minus little a. And then I have, this is a positive c. Oh, sorry, that should be a minus. That should be a minus. I forgot to distribute the negative, right? So that's a minus. That's a minus. There we go. Right, so c minus c is 0. So they cancel. So, yeah, plus 0. All over little b minus little a. All right. So the left side will stay the same for now. And look what I can do on the right side, right? I can factor b squared minus a squared as the difference of squares. B minus a times b plus a. And then capital B times b minus a, right? Over b minus a. And now notice that the b minus a here and here, that's your GCF. That's your common factor, right? So we can factor that out. Again, the left side will stay the same. So we get little b minus a, and then in brackets here we get capital A times b plus a. Well, b plus a is a plus b. Right? It's like 2 plus 3 is 3 plus 2, right? Plus capital B here. All over b minus a. And now that's a product, right? So you see where this is going now, I hope? These cancel. The b minus a's cancel. And now the left side is still 2 times a times little c plus b. The right side is a times a plus b plus b. I think we can subtract the capital B from both sides. And you get 0 on both sides, right? So 2ac is equal to a times a plus b. That's plus b, right? Plus b. So little a plus little b here. Right? And then, well, both sides have a factor of a, so we can divide by capital A. And then that just cancels on both sides. And now we're almost done, right? 2 times little c is just a plus b. So divide by 2, And little c is just a plus b divided by 2. Well, that's exactly what we wanted to show, right? That the midpoint up here, right, is your c. C is the midpoint of a and b. And that does it, right? This is what we wanted to show. So we're done. It's just a lot of algebra here, right? I mean, the calculus part was just taking the derivative. And in fact, because this is just a quadratic function, that should be the easy part. The rest of it was just, factoring and simplifying. And then ultimately just solving for little c here. So we didn't know it at the time, but you're solving for this little c, right? Because the capital C's end up canceling. All right. Again, not an easy problem, right? This is one that you really have to think about a lot. And but it's just knowing the mean value theorem here and applying it to this particular case, and then just simplifying. Anyways, so the whole point of this is that anytime you have a quadratic function, right, let's say we have a parabola, let's say this is the graph of the parabola here, right? And no matter what interval you choose, like let's say this is my a here, and this is my b here, right? That if you connect those 2 points with a line, for the parabola, right, the points where the tangent line matches the secant line will be exactly halfway between the a and the b. That's what this says. Okay? But that's only true for a parabola. That's only true for quadratic functions, right? It's certainly not true for, other functions like sine of x or, x cubed minus x. For other curves and other functions, that's, not going to happen. Or if it does happen, it's a coincidence, or it might happen for, very particular values of a and b, but not in general. For a parabola, it's true in general for any a and b you pick. Okay. Number 17 is the bus problem, and I did one just like that at the very end of the last video, which was section 3.2. So look at that problem and then see if you can do number 17, because it's almost the same problem. The only difference is that in 17, I think the instantaneous velocity turns out to be exactly the average velocity. So in that case, we only expect one moment, one time, where the bus was traveling exactly at 40 miles per hour. Of course, it could happen more than once, but it only needs to happen once in that case. Again, this also has to do with the mean value theorem, which is what we discussed in section 3.2. So I'm not going to do 17, right? Look at the video for 3.2 and look at the end. I do a very similar problem, and that should help you figure out number 17 as well. So that's the practice test. I hope that's good enough as a review for the actual test. You're not likely to see number 16 on the test, right? That would be I would say that's a challenge problem. But I can, maybe ask you a true-false question, right? For a quadratic function, is the value of c from the mean value theorem the same as the midpoint? True or false? Well, after proving this, it's definitely true. So, not something, again, much more of a conceptual question to be able to prove something like this. It's just a lot of algebra. But, a true-false question or a multiple-choice question based on something like this is not unreasonable, because it's a very small part of the test. So, in any event, just make sure, right, I spent a lot of time on number 2 taking derivatives. There'll be a lot of problems where just, here's a function, take its derivative. So make sure you know how to do a lot of those. And then the rest are just applications, slope of the tangent line, related rates, implicit differentiation, all that stuff. Chain rule, right, all that stuff. So best of luck.